Welcome to Brain Vision.
In this problem, we're given that the curve is banked for 20 meters per second motion. So we know if you're moving 20 meters per second, no friction is necessary for you to go around this curve. Now, if you revert to example 5.22, they derive an equation that is the banking angle is equal to the arctan of v squared over g times r. And this is true whenever friction is not necessary to round a curve. And so we can plug in what velocity that is. In our case, it's 20 meters per second and our radius of our curve. And we get that the angle must be 18.79 degrees. That's not the final answer. That's just going to help us in the end. Now we need to draw a new force diagram. In this case, we have our car here. We have our normal force going this way. We have an angle beta here. And we have the vertical component of the normal force, which is in cosine beta. The horizontal component is here, and it's in sine beta. We also have gravity pulling us down, mg. And the car is going to want to go up the ramp this way, which means friction's pointing this way. So this is force of friction. This angle here is also beta, which means that we can break this up into its components too. And so this is force of friction times sine beta. And this part down here is, oh, my pen's glitching out. 1 second. This down here is force of friction cosine beta. So this is kind of messy, so let's just start writing down Newton's second law. Oh, by the way, there's an acceleration, a radial acceleration towards the center of the ramp this way. So now, if I define this to be my x direction and this to be my y direction, then Newton's second law in the x direction gives me n sine beta plus f, which I'm calling capital F, sub little f, times cosine beta is equal to mass times acceleration in the radial direction. And then if I do the same in the y direction, I get n cosine beta minus force of friction sine beta is equal to mg. Now I know that the radial acceleration is v squared over r. And we know that our new v is 1.5 times our old v. So we get that. And then we know that our old v is, well, it's given in the problem. Essentially, this just simplifies to 2.25 times g times tangent beta. We can write it in terms of beta because of this right here. Now, I'm going to plug this into these equations. Whenever I do that, I get n sine beta plus mu s, and here I'm just plugging in the fact that the force of friction is equal to mu s times n. Cosine beta is equal to 2.25 mg tangent beta. And then for my other equation, I get n cosine beta minus mu s n sine beta is equal to mg. Now I have too many unknowns here, but I have two equations, so I can eliminate one of the unknowns. The unknown I'm going to eliminate is n, the normal force. I can do that by dividing these equations. Whenever I divide them, I get a new equation, which is sine beta plus mu s cosine beta divided by cosine beta minus mu s sine beta. And that's equal to 2.25 times tangent of beta. And so this is the equation you get whenever you divide this equation by this equation. You can solve this for mu s. There's a bit of algebra because there's one copy here and one copy here. So you're going to have to multiply this over here and then distribute it throughout and then isolate the terms with the mu s, and then just pretty much you're solving for the coefficient of static friction. And there's about 5 algebraic steps in between. But at this point, you should be comfortable doing that. And when you do that, you get that's equal to 1.25 sine beta cosine beta all over 1 plus 1.25 sine squared beta. And then plugging in the beta we found on the previous page, we get that mu s is equal to 0.34. And that's the final answer.